Okay, so we get a test. So I've got the new schedule up for Unit 2. So next week, Wednesday is the first quiz, the week after is the second quiz, and then Friday is the exam. It's kind of a short unit, but pretty big unit. So takeaways from the reading, like I said, kind of a big day today. Takeaways from the reading. We learned that the slope of the tangent line and the derivative at a location mean the same thing. So we finished Unit 1 off talking about tangent lines and finding their slope. And then Unit 2 started there and said, well, that value, that numeric value, we really call a derivative. And then we came up with, I'm going to use my laser pointer here, but we came up with, probably works if I do this. We came up with all of these right next to the clock. All of these ways we can express in notation what the derivative is. So we've got a ton of different ways. We use probably 2 or 3 of these. We use the dy dx. That's called the Leibniz notation. Kind of looks like a fraction because slope is a fraction. It's a rise over 1, a run. So we have a dy dx. And then we have an f prime of x. So in other words, if we have a function f of x, its derivative, its slope at that point is f prime of x, or we could just use f prime. Those are the 3, and then y prime. Those are the 4 most common notations we'll use. And then we talked about, well, when can we not find a derivative? So it's kind of like with limits. Sometimes they exist, sometimes they don't, right? And limits don't exist with when we have all of these things up here. Same with derivatives. Sometimes they exist, sometimes they don't. And so derivatives don't exist at locations where we have corners because we have 2 sloped things coming together. And if we're right at that corner, it's like, which slope value do you use? You know what I mean? Do you use the negative slope or the positive slope value? Same with the cusp. The cusp is another, I call these pointy points. The cusp is just like a corner, except it's a line coming together with a curve. And then we have a situation where this function goes vertical right here. So it kind of curves up and then it curves flat. And so right at that location where it goes vertical, if we had to draw a tangent line, it would be vertical. And what's the slope of a vertical line? Infinity, right? Doesn't exist. So if the slope doesn't exist, then the derivative can't exist. And then anytime we have a discontinuity, we can't have a derivative. Okay. So so we know we have these points of and it's a really long word. We have these points of non-differentiability. Okay, really long word. In other words, we can't find the derivative. Okay. So I'm going to ask you this question over and over. I say slope, you think derivative, right? And then I'll switch it up. I say derivative, you think, right? Because they are one and the same. They are one and the same. So in the notes for today, we learned how to determine the derivative of linear functions. So if you're going, oh, forgot to take the notes. It's only about 10 minutes of notes. Don't worry, we're going to go through about half of it right now. X equals 5 is what sort of line? What slope does a horizontal line have? 0. So if the slope is 0, then the derivative is 0. When I say slope, you think x equals 8, still a horizontal line. It's up here, right? What's its slope? 0. What's its derivative? Okay, let's look at this line. F of x equals 3x. What's its slope? 3. What's its derivative? F of x is 4x minus 2. What's its slope? 4. What's its derivative? 4. Right? And because those are lines, the slope never changes, no matter where we look at it. That makes sense? So the derivative is never going to change, no matter where we look at it. You can look at it at any point, and the same slope and the same derivative. So far, so good? Okay, so the activity for today then is we have these 4 functions, and we want to come up with the slope at any point for those 4 functions. So this is going to be pod A. This is going to be pod B. Oops. I know you want that. I'm going to do B. This is going to be pod B and C. Excuse me. This is going to be pod D. And for the last time, for the very last time, you are going to do the limit method. So, we know that the limit method involves this long drawn out thing, this long drawn out process of having an f of a plus h and an f of a. Okay, and since these functions are curved, right? These two are quadratic, so they're parabolas, and these are cubic, so they're like to a 3rd power, right? That tangent line is going to change in slope depending upon where you are. So we are going to do the limit method for one last time. Your A is not going to be a specific point though. Your A is going to be the variable x. Okay? And then you are going to apply the definition of the derivative, in other words, the limit method, so that you can find an expression. Okay, so I want you to do this in your pods. So row A, row B, row C, row D, get together, okay, and help each other put x minus h here and square it, and then f of x, and x minus h here and square it. F of x is obviously just what you see. This is just what the chart says. Help each other through with this algebra and this simplification. Okay? So you've got about 10 minutes-ish, call it 10 to 15 to do that. We don't have any topic questions today, so we're not in a huge rush. But we need to make some generalizations here. So go ahead and get together. I don't care if you move the tables to get together in your groups. Okay? If you want to, go right ahead, or if you double up on the tables, either or. All right, so we got through this activity, and a couple of you actually, after you did yours, you took a shot and you just tried to do the other one without doing the limit method, and you're like, oh, this works. So what works without doing the limit method? Huh? Okay, so doubling, like where there's a 1, there's now a 2. Yeah. Okay. Let's see if that works. Where there's a 3, is there now a 6? Where there's a 2, is there now a 4? Where there's a 4, is there now an 8? Where we just doubled everything. Yes. Yeah, right. I should have maybe left it 2, but could you imagine doing something and having to do limit method?
216 on that.
Yeah, right. If I had like 6x cubed plus not 2, then 4x squared minus 7x plus 4. Can you imagine having to put x plus h here and cube it? So recognizing that all we're doing is we're taking that power and bringing it down front. But what happens when the power comes down front and there's not a 1 coefficient? We're multiplying, right? We're still multiplying here. It's just by 1. Can I get anything else in here? It's just by 1, right? So that's how we got our 4. That's how we got our 8. What would this be? 18. So now let's talk about what the new exponent becomes. 18. Yeah, what happened to our exponent? Well, we brought it down, didn't we? So this exponent is, what is the exponent on this? 1, right? So it got smaller by 1. So this is x squared. Exactly. Look at what happened here. Right, the coefficient is 1 here. What's the power here? You brought the power down. What's 1 times 1? What's 1 smaller power than 1? Right? We could have done this. Right? But really, x to the 0, you're gonna have to write. So I wouldn't. Away. Right? 5 is like this. It's like it's a constant, right? And we know constants have no slope. So that term by itself has no slope. So I could have done this, but I don't have to. Does that make sense? So let's finish this off. What is this next term? What is this next term? Here's the power. What is this last term? Do your derivative without doing the limit method. And guess what? If you have this, now I can say, well, what is the derivative when x is equal to 2? What am I going to do? Plug in the 2. Instead of having to put 2 in here, instead of x, and having to do everything all over again. And then if I want to change it to, well, what's the derivative when x is equal to 5? I don't have to do a limit method anymore. I just have to plug in 5 and get another answer. Okay. So our essential question, what shortcut can we replace the limit method with? It's that shortcut. So now we need a name for the shortcut. Did anybody find the name in the book? You guys got all those answers. And I think you have that. Do you have that in your notes? So I'll give you a second to get all those derivatives in your notes. You don't have to do the stuff off to the side if you don't want to. Just finish the table. So we are going to say bye-bye to the limit method. People usually say yes. Yeah, exactly. People are like, they have a whole different wave other than this to say bye-bye to the limit method with. I just don't want to do the wave because, you know, might get some parent phone calls. What?
Crazy.
I don't know. We are going to say goodbye to the limit method. The limit method is going to come into play, though, in this respect. We have to look at this notation and take derivatives. Okay. Now, when we see that notation, we have to realize that you're asking to find the derivative of a function. And I'm going to do that instead. I'm going to do the shortcut instead. Does that make sense? Okay, so we are going to replace the limit method with these 2 rules. One is called the constant rule. That takes care of these things. Constant rule. All right, we get derivatives of a constant. And the other one is called the power rule, where we start moving the powers down. Okay, so taking a derivative is a power reducer. It takes our quadratics and makes them into linears. Okay, it takes our cubics and makes them into quadratics. Okay, they're power reducers. Okay, so the constant rule says if my function is a constant, that's what this is right here. If I take the derivative of my function with respect to its variable, typically it's x, sometimes it's t, because sometimes we make things time-based. And my function is a constant value, its derivative is 0. That's what that's saying. So the derivative of my function with respect to x, if my function is a constant, the derivative is 0. So what's if your function is y equals 3, what's the derivative when x is equal to 7? 0. Okay, the power rule is a little more complicated, but it basically describes symbolically, right, with symbols and variables and stuff, basically describes symbolically what you've been saying the last couple of minutes. If I take the derivative of a function that is x to a power with respect to its variable x, then I bring the power down. Notice it's in front now. And then I reduce the power on the variable by 1. Okay, so derivative of a constant is 0. Derivative of function y prime, derivative of 3 is 0. So anywhere it's 0. Notice the second notation. The first notation just says it's 0 everywhere. The second notation says, well, okay, it's a little weird, but you did ask me about when x is equal to 7. That's just one location on the line, right? Here is y equals 3. Right? Here is y equals 3. Here is x equals 7. It's just saying what's the slope of my line right there? Still 0. How about this example 2? What's the derivative? Notice I'm using different notation just to get you used to it. Now I'm calling it df dx. You could have called it f prime of x. They would even let you call it y prime, even though the y is not in there, it's implied. Anybody want to take a shot at this? What's the first term? 7x to the 6th. Oh, okay, whoops. Well, that's just saying differentiate that. 7x to the 6th. What's the next term? 10x to the 4th. What's the next term? 6x. A little easier than the limit method? Yeah, can you imagine taking x plus h to the 7th power? No, thank you. Okay. That is, so we call this, isn't it just another function? It's a function to the 6th power, right? So derivatives are just nothing more but functions. Right? That's exactly what they are. But now we have an expression that we can use to find the derivative anywhere. I want to find the derivative when x is equal to -1. So I'm going to plug, I guess I didn't show any work out of me. I'm going to plug -1 in there. What happens when I plug -1 to an even power? It's positive, right? So this is 7, another even power. So 7 minus 10, which is how much now? -3, right? And then 6 times -1, that's an odd power, right? So this is actually a -6. So -3 minus 6 is -9. You doing okay? Okay. So this last example is tricky because what we have to do is we have to get the derivative to look like this, x to the n power. There's not a fraction in there. X is in the numerator, not the denominator. Does that make sense? This will work for anything, but we got to make sure that it is written as x to the n power. Okay, and these are not. I want to write the x cubed and the x up in the numerator. What do I have to do to their powers? Make them negative. So the first thing we need to do is what I call a rewrite. I'm not doing any calculus. I'm just rewriting the function in a more convenient form so I can use my shortcuts. So that's 1/5 x to the minus 3. Notice the 5 stays in the bottom, right? We're not moving the 5. We're just moving the variable. And the next one is 8x to the minus 1 power. Now I can do my power rule. So this is where we're going to want to kind of slow down here, right? And make sure we got our steps that we need. Minus 3, bring it down and multiply it times 1/5. What do I get when I bring down the minus 3 and multiply it by 1/5? So in your brain, hopefully you're thinking 1/5 times minus 3 over 1. Right? -3/5. So we're doing that. Now, I will clean it up in just a second. Here's the tricky part. It gets people every year. And if it helps, I've got a number line in the back of the room. What is 1 smaller than -3? -4. I know, it gets people every year. They're like, oh, it's got to be 2. Wait a minute. Right? 1 smaller is moving to the left on the number line. It's -4. It gets people every time. Don't worry about it. Everybody messes that up the first time through. All right, let's do the next term. 8 times -1. That's the old power coming down. What is 1 smaller than -1? I bet you do a lot better now. Right, -2. Okay, you doing okay? Okay, so now I'm going to clean this up. Just like you said a little while ago, that's -3/5. Notice what I did to the x to the -4. I put it back in the bottom and gave it its positive power back. Okay, that's how you're going to see the form of the answer, with positive powers. Okay, even if it means relocating it. Same with the next term. It's going to be minus 8 over x squared. We're going to give it its positive power back. You doing okay? Better than the limit method, though? Okay, here it is. What's the answer to that question? I don't know. Okay, but I know it's asking is the derivative. So somewhere in this expression, I gotta find a function. Okay. So looking at the 1 plus h, that's really just what? Think of that according to this definition, right? This is our definition of our derivative now. We're talking about this. That's just the function at 1, right? 1 plus h. So we really can look at this expression and say that is really just 3x squared minus 4x. That's how we look at that whole notation. It's a daunting notation. It's got lots going on there, and you start to get a little nervous that you might have to do a limit method or something. I'm just asking you to find the function. You can also look next door in the numerator and see the 1s and just replace those with x's. You just have to factor out the minus first. Okay, what's that derivative? Six x minus 4, right? So 6x minus 4. And now what if I want to evaluate it at 1? It's 2, exactly. It's 6 times, so oops, 6 times 1 minus 4, which is 2. Okay. So again, I can't stress it enough. When you see this notation, I don't want you to do the limit method anymore. I do want you to find the function though and use your power rules. Okay, we give you a lot of piecewise functions. We're not going to stop. I'm sorry. We're just going to get you more and more comfortable with them. Okay. So is this differentiable? Okay. So if this is differentiable, then we know that we have to check two things. We have to make sure it's continuous, and we have to make sure the derivatives match. So it's nice and smooth. Okay. So we're going to see if it's continuous. How do we find if it's continuous? We throw in 2. So do that quickly mentally. If I throw 2 in the top and 2 in the bottom, do I get the same number? What is that number? Okay, thank you. So I'm going to throw 2 in the, here's the really fancy way of saying it. I'm going to take the limit as we approach 2 from the small values, which means my top expression. And that equals 9. 17 minus 8 is 9. I'm going to throw 2 in from the larger side, which means using the bottom expression. That's 12 minus 3, which is 9. I could have asked you that question in the last unit because that's just checking continuity. Make sure that we have a make sure that we have the limits coming to the same value, and because of the equal sign in the bottom function, you know the function value is also 9. Now we have to check derivatives and make sure our derivatives match. What is the derivative of the top function? Minus 4, right? It's a linear equation. It's like one of these. Right? We're just looking at the slope value, the m, so to speak. What about the bottom function? What's the derivative of the bottom function? 6. Do those derivatives match? I got one slope coming in and another slope coming out. Does that make sense? When I go into 2? What sort of arrangement do I have in terms of non-differentiability? I have a corner. I got 2 lines coming together. So that means the derivative doesn't exist. And a point of non-differentiability. It's a long word. It's like Mississippi. Non-differentiability. Spell it N-O-N-D-I-F. Done. Non-diff. Yep. Like Mississippi is just M-I-S-S. And everybody else knows what you mean. Yeah. What happens if these derivatives did match? if these matched, then that means I must have had really the same slope line coming through at that point. So it would be differentiable, it'd be nice and smooth there. Or maybe it was a parabola going off to a line nice and smoothly, or vice versa, a line coming into a parabola nice and smoothly. Am I going too fast? Am I going to? I know there's a lot of notation there. We're good? Okay. All right. Instead of the limit method, we use what? Give me something to use. Power rule. There's one other one. Constant rule. That's really kind of a special situation of the power rule. So we're going to stick to those two rules, constant and power. There's other rules. We'll learn those later. Okay. You already did the activity. Big smiley face. There is no topic questions for today. We're going to do them tomorrow. We're going to spend a couple of days here at this on this content. Your notes for tomorrow is to look at a unit circle video. It's not really a whole lot of writing stuff down, but we're heading there. We're heading to trig function, so we need to be familiar with our unit circle values. That's tomorrow. Day 4. Yeah, topic questions. The topic questions are for day 4. They're for tomorrow. Oops. Tomorrow you will also be getting resources to do your test corrections.